Hello, good morning, afternoon, evening, night, whatever or whenever you're watching this, depending on where or when you are. Uh, First of all, of course, I'd like to thank the organizers for allowing me to present you this, to share you this work, and hopefully next year we can all meet in person for a new Friends of Friends meeting. But in the meantime, it's good to be in touch, even if it's so far away. All right, so I'll share my screen and start the presentation. Let's see if this works. All right, so this is the work that I'm going to be presenting. It's the interaction of strong winds in orbit of a supermassive black hole. And it's a collaboration of several researchers here in Mexico. The PI of the project is Verónica Lora, which is at the Instituto de Radioastronomía y Astrofísica in Morelia, Mexico. And there's also work by Alex Raga and myself at the Nuclear Institute, at the Instituto de Ciencias Nucleares at UNAM as well, and Jorge Canto at the Instituto de Astronomía, also in Mexico City. So this work is an extension of a model that was presented by Jorge Canto et al. Back in 2000, and it's basically the wind that it's formed by the interaction of many individual stellar winds. So all these individual stellar winds, as we can see here in the sketch here, they interact and they form a common wind of a star cluster, and it's called a star cluster wind or superstar cluster wind, depending if it's a star cluster or a superstar cluster. And the analytical models are those of a mass-loaded wind, and they predict a profile, a radial profile of density, temperature, velocity, which can be used, for instance, to estimate X-ray luminosities and different things. And back in the day, the results were compared with ROSAT simulations in X-rays and numerical ROSAT observations and numerical simulations of the Archer star cluster. Later on, this model was extended to include not a uniform distribution of stars, but a radial distribution of stars that follow a power law with an index alpha in Rodriguez Gonzalez et al. 2007. However, none of these models included the motion of the stars. It was already a steady state. The stars are in its place and the winds interacting. And this is reasonable in most cases because the wind of each of the stars is of the order of 1,000 kilometers per second, and typically the orbital speeds are much less than that. However, an interesting case is when this is not longer the case. And for instance, if we have a system of stars orbiting a supermassive black hole, such as the one in the center of our galaxy, then the orbital speeds can become of the order of the wind speeds. And well, this is very ad hoc or very appropriate given the Nobel Prize given last year. It's already being noted that the temperature of the gas around Sagittarius A, which is about 40 million Kelvin, it's hard to explain by just the interaction of the winds by themselves. In other words, we need additional sources of energy, and the most obvious one is the orbital energy of those stars that are moving very fast close to the black hole. Of course, there have been a number of numerical studies with different complications and different assumptions, and the most recent one is that of Ressler, Quartet, and Stone in 2018. They model the strongest winds near Sagittarius A, which are 30 Wolf-Rayet type stars. We have very strong winds. They use the Athena code, and they reproduce the orbit of each of the stars. They include radiation cooling and the accretion to the central black hole, and they actually use a fairly good resolution, and they have very, very nice results. Later on, the same authors repeat a similar calculation, but now including the magnetic fields injected by all the stars, and they concluded that basically it wasn't very important. I think the title of the paper was something around on the surprisingly small impact of magnetic fields or something like that. So our work that we're doing here, it's a analytical generalization of the mass-loaded wind presented in Cantu et al. To include the motion of the stars and to include the potential energy injected by the stars and the gravitational force of the central black hole. We also do numerical simulations with the Wacho code, which is a grid-based code that solves the hydrodynamic or magnetohydrodynamic equations, and we couple it to a n-body module or n-body code that became a module of the Wacho to solve the orbits of a number of stars around the supermassive black hole. In particular, we use 100 stars and the supermassive black hole, and we run 3 cases. 2 in which the initial conditions were with the 100 stars in circular orbits, and 1 with eccentric orbits. We do not include radiation cooling in the code, which is really not important given that the time scales are very fast. There's not really enough time to cool efficiently, except maybe for regions very close to the black hole or regions in some particular regions, but in general, it's not really important. And we use the results to compare to estimate X-ray emission, and we compare our results also with more detailed work by Resler et al. In 2018. By the way, the Wacho code, it's available, freely available on GitHub. You can download it from here. If you want to use it, go ahead. If you have some issues with the code, you can just write me an email, and I'll try to do my best to solve doubts, or if you want to collaborate using the code, well, you can also drop an email. So let's start with the analytical model. We consider n stars, all in circular orbits around a supermassive black hole with mass SMBH. All the stars are identical with isotropic winds with a mass loss rate mw dot, a terminal velocity v wind or vw, all uniformly distributed inside a cluster radius rc. So in this case, the mass injection rate per unit volume and time, which we will be calling little m dot, it's well, the total mass injection rate, which is n times big M dot divided by the volume. And we write this as n, little n, which is the density of stars, n over the volume V, times the mass loss rate of an individual star. Of course, the kinetic energy now that is deposited by each of the winds does include an orbital speed. And they added in quadrature, so the velocity squared, it's V wind squared plus V orbital squared, and this is of each of the particles. Now, if we assume circular orbits, and we assume that the supermassive black hole, it's supermassive, so its mass is much larger than each of the stars, then the circular orbit of the stars is simply this circular speed formula, right? The square root of GmbH divided by R. Thus, the kinetic energy injection rate per unit volume becomes 1/2 of m dot w b squared, and then b squared here we can replace the bw squared plus the square root of the orbital speed, so let's just remove the square root here, and we have this expression for the energy injection rate. At the same time, the winds also inject potential energy at a rate E dot potential, which is the total mass injection rate by this times this factor here. So this is just the potential energy because the winds are injecting energy in the computational domain. Now, the mass energy and the mass and energy input rates if we integrate over a given volume, so we only get the mass and energy rate per unit time, we can equate those to the integral over the surface that surrounds the cluster, that bounds the cluster of a radius RC, of the flux of the mass, which is the rho v, and the flux of energy, which is v E plus B. And this is, probably you remember the derivation of the Euler's equations, so it's basically the same. So this is the flux of energy, the flux of mass, and if we integrate those over a surface of a sphere of RC squared, we have something like this. So this is mass conservation. So this is, just the mass, the mass integrate, well, the mass rate, the mass loss rate integrated over volume. So this is just let's say the MDT total, and this is equal to the flux of mass integrated over the sphere of radius r, 4 pi r squared. Same with energy. So this is the volume integral of the energy, the total energy, and this is the surface integral of the energy flux. Now we can also include the equation of motion. So this is just the Newton's second law per unit volume. So this is the rate of change of momentum, and we have here the forces. We have the momentum that is being deposited by the sources. We have the pressure gradient, and we have the gravitational force. Using also the definition of the sound speed, and we can do a little. Actually, not a little, but quite some algebra. We can obtain a differential equation for the velocity inside the cluster radius RC, or outside the cluster of radius RC. We can set n to 0 here, so we don't have injection of momentum, and the mass conservation is just evaluated at RC. So there's no more mass that is being injected. Everything is injected within the sphere RC. So we have a different differential equations for RC. And then we can, of course, you have to match the solutions. And in the paper, there's a good deal of discussion of how to do it, because it's a little tricky. But before that, we can renormalize the equations, writing them in terms of these quantities, which is of course, this is the magic done by Jorge Canto to pick up the right quantities, and then we can add dimensional the equations, and they look very, very well. They look simple, but they're still messy. So basically, we write the distances in terms of this R0, and so we now the way change variables to little r, which is R0 in units of r. U becoming the velocity in units of v naught, which is normalizing in terms of the wind velocity. And for the density, we also have this expression here, and we have these three equations for the solution inside the cluster radius, outside the cluster radius, and they can be solved numerically, but numerically with mathematical, let's say, these radial profiles, and we have something like this. This presents the solution for different RCs, so different sizes of the cluster, and this is the resulting density profile. It has some transition there, and then it follows like a power law. I guess it's 1 over r squared. Then this velocity is also changing, and the sound speed or the temperature inside has this radial dependence. So, okay, so this is the analytical model. We also do numerical simulations. We couple an embodied code originally written by Veronica Lora in 2009 to our own MHD hydrodynamical code Wacho. The embodied code solves the orbits of n stars, in this case 100 stars, around the central object, and it's run at the same time with the hydrocode, and at each time step it passes to the hydrocode the positions of the stars and its velocities, and they used to move the sources of the wind, and also to include the orbital speed of each of the winds that it's been injected in the hydrocode. We also include the gravitational force from each of the sources to the gas. We do not include the gravitational force of the gas to the stars, which is in this case is also not really relevant. We do not include radiation cooling, which is also not very relevant, and we do not include the accretion to the supermassive black hole, which might be relevant, but only very close to the center of the cluster. We use a Cartesian domain of 1.5 times to the 18 centimeters per side. So that's like 0.5 parsecs, and it is discretized by 600 cells per side. The supermassive black hole has a mass of about 4 million solar masses, and all the stars inject identical winds. All the stars have a mass of 1 solar mass. The terminal wind velocity is 1,000 kilometers per second. The temperature is 10 to the 5, and they have a mass loss rate of about 10 to the minus 6 solar masses per year. All the stars are distributed within a radius RC, which in this case was 0.1 parsecs, which including the supermassive black hole and then this number and the orbital speed. It's an RC, a critical R of about 5 inside RC, and outside the medium has a uniform density about this one, like 1 particle per centimeter, and a temperature of 10,000 Kelvin. And we run 3 models, one with circular orbits and this cluster radius, one with eccentric orbits and the same cluster radius, and an additional one with circular orbits and half that cluster radius. So instead of 0.1 parsecs, it was 0.05 parsecs. I will show now a rendering or animation of the cluster. Here we have 100 sources, and we can see how they move and how they inject their winds, and they produce this crazy structure. So this is density with some sort of transparency. It's more transparent when it's less dense. It's more opaque and more bright when it's more dense. So let me just put play to it. We see each, now we'll pause it, each of those little things with those like rings around it. It's a source of wind, and this is just the wind that has some structure to it, and they orbit around each other. This is one of the cases with the eccentric orbit. So this stars it's moving away, but it will come back. This is the elliptical orbits one, and on average the RC it's 0.1 parsecs, but some 1 or 2 stars will go away and come inside. But we do reach some steady state after some time, and even if it does look messy, I hope it's not too pixelated in the video. But okay, I'll show you. So you can see it's a little messy. It's formed a little turbulence inside, but it has some radial profiles, and they do coincide a little bit. You'll see in a moment with the vertical models here. Oh, this is taking a little too much. Okay, I'll let it go. I guess it's too much. I can just, I move it faster. It goes like that, like for a long time. All right. So just to be a little more quantitative, we estimate the temperature inside 3 spheres, like say inside 0.1 parsecs. This is the temperature distribution. The circular, this is the case, right? The circular orbits model, when all the stars are placed within 0.05 parsecs, has a higher temperature, and this is to be expected because the winds interact very strongly with each other because the stars are very close to each other, and so they heat up quite a bit. In the cases with circular orbits, which are the blue lines, and elliptical orbits, which is the magenta line, I would say on average they reach about the same value, maybe a little higher on the circular orbits here inside 0.05 parsecs, or very close to the center. It's also a little over the elliptical orbits model. But maybe this one is already affected by maybe in this region, maybe the accretion of the black hole can be of importance. Not in this one. In this one, it's fairly okay. So we can see that we reach some steady state or quasi steady state about after, let's say, 2,000 years, not 200 years, about 0.2 kilo years. In the next slide, I show you a density cut in the midplane, in the Y0 cut. This is the XZ plane, and have 4 panels corresponding to 10, 100, 500, and 1,000 years. And this is just showing a little piece of the midplane cut. So you can see that after maybe sometime between here and here, they reach some steady state. The density, it's about, comparable. If we take a radial average, I would say it's probably the same here and here. So this is the model with circular orbits, with elliptical orbits. You can see there's some stars outside the cluster radius that is marked here with a dashed line. But this start, it's an eccentric orbit. It will go away and then we move in. The temperature looks like this. In the interaction region, the temperatures can reach easily 10 to the 7, 10 to the 8 Kelvin. But after initial transient, they reach a state in which the temperature is about 10 to the 6, let's say, outside the cluster radius. And of course, it falls with radius. In the next slide, I'll show you the comparison between the analytical solution, which is this black line here, and the solution of the numerical simulation. So in blue is the circular orbits, and in the purple is the elliptical orbits. These are all for the cases of RC about 5.8, I think. So okay, so this is encouraging. We have a nice correspondence between the velocity of the analytical solution and the model. Density, temperature, maybe it's a little off, but it's still in the same zip code at least. And the sound speed is also in visual local agreement. Now we calculate the X-ray emission, and the way we do it is basically for a given temperature, we have a emissivity of X-rays in 2 bands, soft band and hard band, between 0.5 and 2 kilo electron volts, and hard band between 2 and 8 kilo electron volts. And we assume that the emission is optically thin, that the plasma is in coronal equilibrium, and therefore we can use Chianti library to calculate the X-ray emissivity in these 2 energy bands as a function of temperature. With this assumption that this in the low density regime and is optically thin, then the flux is proportional to n squared, the local density squared, and the emission coefficient given by the temperature at each point. So this is how the X-ray emission looks. In colors is the soft X-ray band, and contours is the hard X-ray band. Basically, we have an extended emission in soft X-rays, and some X-ray emission that it's a little more concentrated to the center of the stars, to the center of the cluster, and it's stronger, especially the hard X-ray emission in the zone of interaction between the models, between the wings of each of the stars. We also do a comparison with the results of Ressler et al. So this pointed, these dashed lines is their simulation that included cooling and has a lot more resolution than ours, and included also the equation of the black hole. And in solid lines is the analytical model using an RC of 11.9, which is corresponding to the radius of when they impose their sources. And you can see, well, inside RC, they have some differences, but outside RC, the model, I mean, given the assumptions of the model, I would say it's a really, really good correspondence, which is nice because it means that basically that the structure or the average radial structure of this object is basically determined by the input energy rather than the details of the particular orbits or even the accretion of the central black hole. Okay, so I'll summarize here. We develop a analytical model of this mass loaded flow from a wind formed by star cluster, including the orbital motion and the potential energy of the central object and of the winds that are depositing also potential energy. We do simulations of an n-body plus hydrodynamic grid code to solve the interaction of 100 stars orbiting our supermassive black hole. Well, 100, and then we repeat also for the stars. That's in the paper. About the interaction of 100 stars and orbiting the supermassive black hole. The analytical model predicted radial profiles, and they agree fairly well with the simulations. We also calculate the X-ray maps and compare our results with those of Xray et al. 2018, having a good agreement. So as I was saying, the general properties can be estimated by the analytical model without needing to run this fairly super high resolution for a particular object, and the flow properties at least for large radii are determined by the energy input rather than the details of each orbit and the accretion to the central object. I'll show the references here, and I'm running out of time, so you can pause them and write the bibliography if you want. Okay, well, it was a little weird talking to myself. Hopefully we'll see you in the discussion section, and well, thank you for watching this. Goodbye.